Welcome back everyone. Today we're going to do a video about MOSFETs, all about MOSFETs. P-channel MOSFETs like this one and in-channel MOSFETs like this one. We're going to talk about how they work. We're going to do 4 different kinds of circuits, and most importantly we're going to do one about active braking. So this video is really good for anyone that's interested in thermoelectric cooling and wants to turn a TEC on and off. You can use a MOSFET, certainly the cheapest way to do it. For Nerf, that's the way we should be powering our brushed motors, and that is how we should be controlling our AEG airsoft guns. And we all want to know about active braking for airsoft and Nerf. Now when it comes to Nerf, you need to make sure that we have active braking, otherwise we will keep shooting thousands of darts when you let go of the trigger, and something similar happens with AEG. So why do we want to use one of these over a simple switch? Well, when it comes to Nerf, the stock switch, my highly gutted regulator, is this tiny little thing here. And we all know that if you try and put any kind of high current through it, basically Module Blaster, this thing just dies. So people remove that and they will, the regulator doesn't have the switch here, but on like this Nerf and Stryfe, they will cut huge chunks out of here and get hot melt glue and glue in a laughably more powerful 10 amp micro switch. Now using a MOSFET is actually far simpler than trying to cut and glue. You need more tools. You need a Dremel for cutting, a hot melt gun glue, if I can get that out. My mouth is stuck with all the glue in it. Whereas a MOSFET, all you need to do is solder, and this will pass way more current than your little micro switch. But I understand that it's a little bit grey on how MOSFETs work, so that's what we're going to do. As I said, I've got 4 circuits, and we're going to start off with the simplest and work our way through to the most complex, which is the active braking. So I guess, what is a MOSFET? A MOSFET, you need to know about it is it has 3 pins. The first one, or the left one, which is always going to be yellow in our case, is the gate, and that is literally the gate that opens the switch, just like this. It's the rocker. Well, I guess some people might say it's not literally, but that is the switch. And then you have the drain. The drain goes to what you're going to power, which will be the motor, and the source goes to the source of the input power, so your battery. Now this particular one is a P-channel one. P-channel ones are uncommon. They're normally well, I don't know if you call them uncommon. It is normal to use an in-channel MOSFET. They are more common and cheaper, I believe. I don't know if they actually are cheaper, I'm just going to say that. They certainly seem to have lower resistance, be more availability than P-channel ones. So we can use, the great thing about MOSFETs is that you can power 2 different circuits with them. Well, you don't really power 2 different circuits, you can split the circuit. So what that means is that you can have this channel here, which is the switch, which has no current going through it. Well, not no current, but not the motor's current going through it. And you can turn this other completely separate circuit on. And this is really great because that means we can retain our useless little switches in the stock form and just use them to turn on this much more powerful other circuit via the MOSFET. Now I will show you that we have 2 separate circuits going here. Hopefully. Wow. Okay, common ground. This one here is 7.7 volts. Yep, that's better. And this one over here is 5 volts. So we have 2 different circuits here. We have 5 volts turning on the 7 volt. Now when it comes to AEGs and Nerf, you probably aren't going to have 2 separate circuits. You're not going to have a high voltage and a low voltage circuit. You're only going to have one in power from your battery, and we can do that, and that's perfectly fine. So that's currently, obviously it works, switch. That's applying 5 volts to the gate, and that is turning on 7.7 volts. If we are to screw them together, so we now have 7.7 going to the motor and 7.7 going to the gate via the switch. It still works. So that's normally how you're probably going to wire this with a AEG or a Stryfe. However, if you have 2 completely separate circuits, input voltages, this might be, I would consider this to be the Arduino output in this example. Because of course we certainly can't put our 160 amps or whatever it's going to be through the Arduino to power a motor. Okay, you take the gate, which is always going to be yellow in our example. You solder one end to the switch and the other end to the positive input, which, like I said, can be a completely separate voltage, or it can be your source input voltage from your battery. You then have the drain, which is the white one, and that is the negative going to the motor. The positive goes to the input voltage, your battery, and then the source goes to the common ground of your battery. And so this yellow wire, or this switch, turns the switch on between the D and the S. Now we have a resistor. What is the point of the resistor? The resistor is quite important because the MOSFET has a certain amount of capacitance. What that basically means is that if you turn this on and off, you expect it to turn off when you turn it off and turn it on when you turn it on. Without the resistor, that can stay running because there's a certain amount of charge stays in the MOSFET. So when you turn it off, it may continue going, it may not. You'll get crazy things happening where possibly if you touched it, it'll keep running, or it might go on and off. So you definitely need the resistor there to pull the voltage down to ground for a in-channel MOSFET, which is what this one here is. So that basically means that the default state is off. So that is the simplest form of a wiring for a MOSFET. Now you will find that there'll be a whole bunch of people going, where is the rest of the stuff? And we're going to move to that more complicated wiring diagram now and talk about what you need to do. But this is the simplistic form. This will work, but may have issues, which we'll talk about on the next diagram. So we'll do that one now. Okay, now we've got what is effectively the same basic circuit, but we've added a few things. It still works. Switch, motor on, motor off. But we've added 2 additional things. We've added a diode across the motor, and we have added a resistor on the gate. So it's a good time to talk about resistors. Now we have a resistor bringing this down to ground that we talked about before. We didn't actually talk about the values. Generally that's a fairly high-ish K value because the storage capacity of the gate is very small, so you can have a very high resistance level. When I was turning on really large MOSFETs in parallel to each other to turn on huge loads, I actually had to have a relatively low value of 220 ohms because I only used one resistor for all of the MOSFETs, and I found that running high 10k ones or 100k ones, that actually meant the gates weren't closing quick enough and actually resulted in significant heating. But I doubt that anyone will realistically have that problem, so 10k, 100k, 2200k, which I think is what I'm currently using, will be fine. So that's that one there. We then have this resistor here. What is the purpose of this? Well, that effectively has two purposes. That will slow down the rate in which the capacitance of the gate is charged. So if you slow down the rate that the gate is charged, it'll slow down the opening and the closing of the gate. You generally want that if you have lots of MOSFETs next to each other. What you can get is that, believe it or not, you can get one that's like, I don't know what the numbers will be, nanoseconds, probably less than that, where one MOSFET actually turns on before the rest of them, and therefore all the load goes through the one that's on and the other ones don't really do anything and that one dies. So that's when slowing down the opening and closing of the gate can really help. Well, opening of the gate. So that's normally a fairly low resistance of about 47 ohms, could be less, could be more. The other reason for that is to help with ringing, which you should never get in our basic wiring with our simple battery switch MOSFET. And ringing is basically interference from other components, which, although people think this should be off, it's actually not, and you get a bit of ringing turning on and off and not staying on and not staying off, and you get a bit of a painful situation. So that's what it's for. I personally will be surprised if I will use a resistor on the gate in any of my simple designs. The other thing you could say is that because it slows down the gate, it slows down, sometimes you can, I think, damage that by allowing that to charge too fast, but I haven't found that to be the case in my little budget designs. But certainly if you want to put a resistor on there, you certainly can. That's why it's there. That is technically the correct way to do it. So put one on there, but you probably won't see me doing it because my entire process is to be as simple as possible to get it to work. Okay, there goes a random bug. Here we go, random. Okay, moving on to the diode, which is a bit hard to see which way around it is. The line is on the positive and on the negative. Now the point of a diode is it only lets power go one way, which is great. Now of course it's currently blocking power, otherwise it would bypass the motor and the motor wouldn't turn. And now the motor's off and you think, well, this is the most pointless addition you could ever come up with because it does absolutely nothing. Well, yes and no. So the purpose of that is it's called a flyback diode, but honestly there's I think about 5, 6, 7, 8 other names for it. And what that is about is that the motor is an inductor, and inductors, which basically means a big coil of wire. If you've ever taken a motor apart, that's what's in it, big coil of wire. There we go, big coil of wire. Well, I guess that's not a big coil, but that is certainly a coil of wire. And believe it or not, you actually cannot turn electricity on and off instantaneously. So what happens is when you turn this switch, which turns this gate, closes that gate, the voltage builds up into quite a large number. I mean, it depends on a number of factors, so I can't give you an actual number. And so what that can mean is you can actually, it'll feed it back into the what do we got? The drain of the MOSFET. And if that voltage spike created gets too large, it will actually destroy the MOSFET and you'll have craziness going on. So you add a diode, so when the motor is turned off, but it's still spinning and creating this back EMF and inductance, it doesn't create this huge voltage spike which can destroy your MOSFET. So what that happens is it still manages to conduct the power along the diode as if you hadn't turned that off. Now that's a version of explaining it, but there's a really good explanation I found from someone else's YouTube channel, so I'm going to chuck that up now, and that's much better. He whips out his oscilloscope and blah blah blah. I was going to try and do that because I do have an oscilloscope, but it would make it longer, and he does a good job of it because he actually knows what he's talking about, not me. Well, I'm trying to sound like what I'm talking about. Sound like what I'm talking about? Exactly. I guess that proved my point. So that is the diode. So you should have that. Whether or not you need that or not is a debate. It's easiest just to put it on there across the motor. I mean, because of course you can put it further down the wires. You don't have to put it on the motor. But in theory, you could say if you test it, and if the voltage spike is not greater than the, I've just forgotten what it is, the breakdown voltage. There we go. Yeah, hammer time, breakdown. Because no one's going to be old enough to know who he was. Then it shouldn't destroy the MOSFET. So that is also the correct way to do it, but it will work without it. And if you are switching something that's not an inductor basically means a motor. I know that's not the total truth, but it's a simple thing. All electric motors are inductors as far as I'm aware. Or brushed ones anyway. Then you should have a diode. But if you're switching some other circuit on and off with the MOSFET and it doesn't have significant inductance, then you don't need that. Okay, so this is for the pedantic people that want the perfect circuit. You should do it like this. Okay, cool. I'm probably not going to do it like that. Probably will have a diode across it though. But that is essentially the same with the addition of a resistor and a diode, and that's what they're for. We're now going to move on to a big channel MOSFET. Okay. Oh, it looks, well, actually, I was going to say it looks exactly the same, and it would look exactly the same if I had them in the same packages, but in this case, this is bigger. So, the important thing to notice is that the MOSFET is in the negative line, or the ground line, and that is what is getting switched off, on and off, the negative going to the motor. And you are applying positive voltage to the gate, and that works happily. So now we'll move over to a P-channel example. Okay, now we have our P-channel MOSFET. It's got the same resistor from the gate to the source, and I've decided to keep the coloring of the wiring exactly the same, so you can see that on the actual inputs it's ended up being different. So before we were applying positive through our switch, we're now putting a negative through our switch, and our MOSFET is now taking the positive through it and switching the positive and sending that to the motor, and then the ground is actually this red one. I considered wiring it the right colors, but then you might be like, well, that looks exactly the same to me. So now you can tell that there is a difference. So this is a P-channel MOSFET. It works. So now what we're going to do is we will put them together, a P-channel MOSFET and a N-channel MOSFET, and we will do active braking, which is probably what you've all been waiting for. Woohoo! Let's do that now. Okay, so here we have them combined. We've got our N-channel MOSFET and our P-channel MOSFET, and this is the simplest way that I could come up with to do motor braking. So the power, or the going mode, is still handled by the N-channel MOSFET, and the braking is now handled by the P. So you could say that the sizes are the wrong way around, but whatever. So it's fairly simple. We still have the switch, which is going to the battery input. There's only one circuit if you like, because that's how people will do it. It's then going to the gate of the N channel and also the gate on the P channel. We then have the drain is going to the motor, and it's also going to the P channel, or you could say the gate and the drains on the MOSFETs are basically stuck together. Well, obviously the gate and the drain and the drain, not the gate and the drain stuck together, because that would be a big waste of time. but you get it. And then it's really not that hard. Then all you have is the positive coming in from your battery, and the negative also going to the positive, well, from a color point of view, the black going to the same positive line, and now you have active braking. And what that is you have instant acceleration on and instant stop. Instant on, whoa, instant stop. Let's try that again. And that's very good for your Nerf guns if you're using it to power the motor which pushes the darts out. If you don't have active braking on, then when you take your finger off the accelerator, or the accelerator, it's not a car, off the trigger, then it will continue to shoot darts slower and slower, and normally ends up one getting kind of stuck in the flywheels or whatever. And AEG Airsoft stuff, it's got something to do with how it primes the piston. You want it to stop and start quickly. One word on that is that when the braking happens, all of the heat is dissipated into the motor, so the motor will get a lot hotter. And for a little motor like this, it doesn't really matter, but if it's a big powerful motor, then it will matter. And we don't have a flyback diode. I don't believe we need a flyback diode because we're just shorting that inductance out and causing the motor to stop, and the back EMF, really the back EMF that you're then using to stop the motor. So we don't need a flyback diode if we're doing active braking, and we don't need the other resistor. We've just broken off the wire, but that's it, guys. Hopefully you've enjoyed that. I've got a Facebook page which is pretty active about more complex wiring than I do here, and crazy awesome stuff that you guys like to do, and questions, so join up to that and we can be making stuff awesome together. Subscribe if you like it, subscribe if you didn't like it, give me a thumbs up if you liked it, and a thumbs down. No, never do that. That's just sad faces. Don't do that to people. Alright guys, there we go, active braking, awesomeness. Soup.